forgot we have quite a few people from Wanakee in this class. Yep. All right, continuing on, we have 3 more sections of work to do in this class. We'll pace this out a little bit. Get to a nice little conclusion point here. And QED, call of the day. Welcome to May. It is near the end. These last 3 or 4 weeks will go very fast for us. We're going to continue with the idea of series and sequences. But today what we're going to talk about is we're going to talk about infinite series. The work with infinite series key as we get into May here. Keep up with the material. A lot of distractions that are there. We have problems. We have all kinds of stuff going on here. A lot of distractions, but continue to keep up with the material that you have, your educational responsibilities. Please keep up with them. Infinite series, when we talk about an infinite series, it is the sum of the terms of an infinite sequence. Okay, once again, an infinite sequence is an infinite number of terms. And when you're adding up the number of terms of an infinite sequence, that's called an infinite series. Now, 2 things are going to occur. The one aspect is going to be it's going to be a convergent series. And when you talk about a convergent series is an infinite series that sums to a total. You'll be able to get a value. This is called a convergent series. It converges, it gets closer to a value. When you converge on something, you're getting closer and closer to it, so you have an exact value. You have also a divergent series, which is what people typically think is going to happen is it doesn't come up to a value. It continues to get bigger and bigger and bigger. The infinite series that does not sum to a total, it just continues to get bigger. It continues to get bigger. It goes towards infinity. The first series, the infinite series we're going to take a look at is an infinite arithmetic series. 1 plus 4 plus 7 plus 10 plus 13 plus 16. We continue to add 3. We have an infinite series. We have an arithmetic series. Common difference is a value of 3. 4 minus 1, 7 minus 4, 10 minus 7, so on. We get a value of 3. Well, if we add the first 2 terms, the sum of my first 2 terms is a value of 5. Adding 1 plus 4 together to get a value of 5. The sum of the first 3 terms is 1 plus 4 plus 7. That gives me a value of 12. The sum of my first 4 terms, I add a value of 10 in there, so we get 22. My sum of my first 5 terms, I add 13 to that, I get a value of 35. And as I can see, if I add another term, it's just going to continue to get bigger and bigger and bigger and bigger. I go from 5 to 12 to 22 to 35. My next term I'd add in there would be 16. I would get a value of 41. Okay, the values continue to get bigger. The sum of my series continues to get bigger. So as my term numbers get bigger, my total gets bigger and bigger. So what we come out to is a divergent series. Because as my number of terms get bigger, my sum gets bigger. Even if I had a ratio of just 0.5, if I had 1 plus 1.5 plus 2 plus 2.5 plus 3, even if I had a series with my common difference of 0.5, as I would add in the next term, my sum would continue to get bigger and bigger and bigger and bigger. So for any infinite arithmetic series, you'll be divergent. For any infinite arithmetic series. If we take a look at a geometric series, okay, we have 3 plus 6 plus 12 plus 24. We have a common ratio of a value of 2. Also up here, if I take a look at my terms here, or how I do my sum, I have my term numbers times Tn plus T1 divided by 2, my average of my first and last term, multiplied by my total number of terms. My term numbers will continue to get bigger. That average will continue to get bigger. These values all go towards infinity. But if I take a look at my geometric series, my sum of my first 2 terms is a value of 9. 3 plus 6 is a value of 9. My sum of my first 3 terms, I would add 12 to that, would give me 21. My sum of my first 4 terms, I would add 24 to that, I would get 45. If I add the sum of my first 5 terms, I would add 48 to that. That would give me 93. And once again, as you can see, what is occurring here, as my sum gets bigger and bigger, or my total number of terms get bigger and bigger, my sum continues to get bigger and bigger and bigger. I go from 9 to 21 to 45 to 93. So in this situation, I have a divergent series also. Well, you may be sitting there thinking to yourself, well, mathematically, if I have an infinite number of terms, and I'm adding an infinite number of terms together, my sum is always going to get bigger and bigger and bigger. Why? Because I have an infinite number of terms. So my sum's going to continue to get bigger and bigger and bigger. Well, let's take a look at the last scenario here. We still have a geometric series. But now my common ratio is a value of 1/2. If I take the sum of my first 2 terms, I get a value of 36. The sum of my first 3 terms, I add 6 to this, I would get 42. The sum of my first 4 terms, I would add 3 to that, I would get 45. The sum of my first 5 terms, I would add, let's see, I would add 1.5. So I get 46.5. Sum of my first 6 terms, I would add in a 0.75. So I'd have 47.25. Now I'm going to take half of 0.75, I would get 0.375. So I'd have, 47.625. Then I would add into that 0.18, I don't know, whatever. My brain's not working too well. It's a Monday morning. It's May 2nd. But as we can see what is occurring here, as I add more and more terms, my number is not getting bigger and bigger and bigger. It's not going towards infinity like my other ones were. I was going 9, 21, 45, 93. It just keeps on getting bigger and bigger and bigger. Or I had a value 5, 12, 22, 35. My numbers were just getting bigger and bigger and bigger. But with this last one, my number is not continuing to get bigger and bigger and bigger, because I'm going to add in another decimal that's 0.1875 or whatever it is, and then I'm going to get a 0.09 I'm going to add into that. Then I'm going to get a 0.0045 I'm adding into that. So what I'm adding to my total, the number continues to get smaller and smaller and smaller and smaller. So I don't have these scenarios here with the divergent as the sum continues to get bigger. Okay, as I add in more terms, my sum just continues to get bigger and bigger and bigger. That's divergent. But now it's not divergent. It's not getting bigger and bigger and bigger. It converges on a value. Well, let's take a look how we find the sum. How do I find the sum of a geometric series? We take our first term and multiply it by 1 minus r to the nth and divide that by 1 minus r. That's the sum of an infinite geometric series. It's what we worked on last week. We take our first term, multiply by 1 minus r to the nth over 1 minus r. Well, if we took a look at the scenario that we had up above with my ratio of 2, I get 1 minus 2 to the nth power. N keeps on getting bigger and bigger and bigger, so 2 to the nth is just going to keep on getting bigger, bigger, bigger also. I'm taking a value of 2 and taking it to a larger value. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. This number continues to get bigger and bigger and bigger. But just look what happens when my ratio is 1/2. What I'm doing here is I'm increasing n. N is getting bigger and bigger. N is 2, N is 3, N is 4, N is 5, N is 6, N is 7, N is 8. Well, in my calculator, what I want you to do is take 0.5 to the 4th power. Then right below that, take 0.4 to the 8th power. And then right below that, take 0.5 to the 16th power. What is happening to this 0.5 to the nth power? What's happening to this value as I take it to a larger exponent, Jack? It's getting smaller and smaller. If I would take 0.5 to the 20th power, and then 0.5 to the 40th power, I start getting scientific notation, e to the negative 12th, negative 14th, negative 16th power. It's getting smaller and smaller and smaller, which means as it gets smaller and smaller and smaller, well, what if I have 0.5 to the 100th power? What if I'm taking the sum of the first 100 terms? The sum of the first 100 terms. I would have 0.5 to the 100th power. This number is getting closer and closer and closer to what value? Todd? 0. It's getting closer and closer and closer to a value of 0. So this value here is getting closer to 0. So I have 1 minus 0, which the last time I checked, hold on, get my calculator out. 1 minus 0 is still a value of 1. So I have my first term times a value of 1 over 1 minus my ratio. So my first term is a value of 24. I get 1 minus, well, if I take 0.5 to a big number, that's going to come down to 0. So as I get bigger and bigger, this value here goes towards 0. So we're left with 24 divided by the quantity 1 minus 0.5. Which is a value of 1. 24 divided by 1 minus the quantity, or divided by the quantity of 1 minus 0.5. What do we get? 48. We get a number. Do we ever reach 48? The answer is no. But it converges on 48. As n gets bigger and bigger and bigger, my sum gets closer and closer and closer to 48. This is what we call, when we get into the calculus world, the idea of a limit. Okay, and you juniors, or if you go into college and you get into calculus, you're going to get into the idea of limits. What's one of the, after you do a little bit of review of some of the ideas in the first week of calculus, you go into the idea of what is called limits. And this is the idea of a limit. As n gets bigger and bigger and bigger, my value or my sum here will converge and get closer and closer and closer to 48. Once again, you won't actually get there. You get 47.999999999999999, but never make it to 48. You add in another term, you add on another 0.9 at the end. You get closer and closer and closer to it, but you never quite achieve it. When you talk about an infinite arithmetic sequence, once again, when we're talking about infinite, and it's arithmetic, you will be divergent. Now, the difference between what we did between geometric, here my ratio was 2, here my ratio is 1/2. If I take a value between 0 and 1, or negative 1 and 1, does not matter. 0 and negative 1, 0 and 1. And I take it to a large exponent. Your number will get smaller and smaller and smaller and smaller. If you take a value that's greater than the value of 1 and you take it to a larger exponent, the number is going to continue to get larger and larger and larger and larger. If I take 1.1 to the 20th power or 1.1 to the 50th power, that number is going to continue to get larger. But if I take 0.9, if I take 0.9 to the 20th power, then 0.9 to the 40th power, then 0.9 to the 60th power, that number will continue to get smaller and smaller and smaller and smaller. So your key here is the idea of a ratio. When you have an infinite geometric series and the absolute value of the ratio is greater than 1, you still will be divergent. But when this absolute value of the ratio is smaller than the value of 1, the sum of your terms will be your first term divided by 1 minus your ratio. But your absolute value of the ratio must be less than the value of 1. So when you have a geometric series, you have to take a look at your ratio. What's my ratio? If it's greater than 1, it's divergent. If my ratio is less than the value of 1, then I can find the sum of my terms by taking my first term and divide it by 1 minus my ratio. Because once again, what occurs here is this 1 minus r to the nth that we talked about and dealt with up till now goes to a value of 1 minus 0, which is a value of 1. So we talk about series. You have 3 scenarios that's going to happen here. We have infinite arithmetic and infinite geometric. Ratio greater than 1, those are both divergent. Infinite geometric, absolute value of the ratio is less than 1. We have convergent. Converges on a value. Once again, we never quite achieve that value, but we'll get closer and closer and closer to that value. The other thing we get to worry about here and work with is the idea of factorials. As we talked about in stats class, we've dealt with the value of, hey! It's a Monday, we need to wake up a little bit here. And when we talk about the value of n, this is n factorial. It's a Monday. The sun is shining. We got 4 weeks, which is really 3 weeks, which is almost 2 weeks to the end of the year. N must be a counting number, which means, I guess it could be a whole number. 0, 1, 2, 3, and so on. And how we calculate N! This is calculated by taking the value of n, which is what you're taking the factorial of, then multiply it by that number minus 1, then that number minus 2, minus 3, and so on, all the way down to the value of 1. My goal here is someday when you're sitting in a boring math class in college, if you have to take a math class in college, and you see a factorial there, there's something in the back of your brain that is screaming at you, and you get a little smile as you're sitting there bored to death in that math class. And you think back to your fond memories, your comfy confines of Downton High School. When you take a look at 7, This means we're taking 7 times 6 times 5. We keep dropping by 1 all the way down to a value of 1. Which I can in my calculator if I want to. 7 times 6 times 5 times 4 times 3 times. Hello, Mr. Black. How are we doing this morning?
Great. How are you?
Doing well. Did you have a good weekend?
I did. Sorry to interrupt.
Did you get some baseball going on this weekend? Huh? You got Cy Young on the mound?
Got rained out on Saturday.
Did it rain on Saturday?
Saturday morning. Big puddles on the field.
What'd you do? You go out there and turn on the sprinkling system?
No,
We played baseball here. You should have been out there getting the field ready for you.
Yeah.
A good coach would have
You're right. Good one would have.
had that taken care of. Now, in your calculator, if you go to your math button, you go to your math button, hit your left arrow. Hit your left arrow. Option number 4, if I'm not correct, will give you the factorials. Now, some of your calculators are old school calculators. You have to type your number in first, so you have to type in the 7. Then you have to go to math button, hit your left button, go to option 4, that gives you 7 factorial. Other ones, the newer fangled ones, will give you a box. So you just go to you find it in your calculator, and then you have to fill in the box. In the case, Cole, what do we come up with? Todd, what do you come up with? If we find the value of 5! Some of you may have PTSD after this, huh? Don't need your caffeine in here. We take 5 times 4 times 3 times 2, we should come down to 120. Once again, we can find 0! And you come down to a value of 1. Now, we want to be able to simplify these. Once again, yes, I can write it out, and yes, I can clickety-clack in my calculator, 5 divided by 7, and come up with a decimal. But I don't want decimals as solutions. So we need to know how to simplify. We have all multiplication here. What we learned in 5th and 6th grade mathematics, when we have multiplication, we can simplify our fractions down. We can cancel each one of these out. They all turn into 1s. So we have 1s all across the top multiplied, and then 7 times 6 on the bottom. I want fractions. I don't want decimals. Now, what you can also look at with respect to this, when I have 3 divided by 8, I can leave that on top and go 8 times 7 times 6 times 5 times 4 times 3 on the bottom, and the 2 3's will cancel out. Because if we have 3's, we have 3 times 2 times 1, 3 times 2 times 1, they will cancel. Hello, Mr. McFerrin. How are we doing today?
Fine.
You having a good weekend? You have a good weekend?
I'd say it was okay. You?
The sun's out.
Beautiful day.
There we go.
Get after it.
So I can cancel out my 3's. So on the bottom, now I'm just multiplying 8 times 7 times 6 times 5 times 4. Once again, if you hit your math button, hit enter, and you dealt with a fraction here, I don't know if it's going to come back to a fraction for you. So you're going to have to go old school here at this point. Lexi, what do you come up with? 6,000 what? 6,720. Like I said, I don't know if your calculator will take you back to that. Because if I go down here and talk about n divided by n minus 1, now we don't have clickety-clack in our calculator. All we have is, once again, what you can always go back to in the math world is definitions. By definition, on top I have n times n minus 1 times n minus 2, and so on. Why? Because that is a definition. That is your definition. The people that are at Wanakee this week, I forgot. They'll be sitting there, maybe looking at the videos, and all of a sudden, they'll get the effect of the class. But if I take a look at the bottom, n minus 1, I start out with what I have here. What is our next term? Courtney, what's our next term? N minus 2. I take my previous term, I have to subtract 1 from that. So that would give me n minus 2, and so on. No matter what the value of n is, the n minus 2's would cancel out, the n minus 1's would cancel, and all these will cancel. The dots will cancel, leaving us just with a value of n. Go ahead and simplify the next one. I have x plus 1 divided by I'm losing my voice. Divided by x. What would that simplify down to? And check your answer with somebody around you. Go ahead to the next two. Quentin, what do you get for the first one? X plus 1. The x's cancel, the x minus 1s, and all these will cancel out, leaving us with just x plus 1. Okay, once again, we are subtracting 1 to get to the next term. Second one, what do we come down to with the second one here? Brandon Shannon, what do you get? X minus 1. Where the x minus 2's cancel, and all these will all cancel out, leaving us just one term, x minus 1 up top. Once again, need to be able to simplify by looking at definitions mathematically, as we've talked about numerous times. You can always go back to the idea of definitions, okay, and utilize the idea of definitions to be able to solve problems. Okay, you have a worksheet here. It deals with some infinite series on top, on the front. On the back side, you have the idea of some factorials. Working with factorials. Tomorrow we'll look at the idea of some repeating decimals. Working with repeating decimals, how we convert them back into fractions. And then the last topic we cover is working with sigma notation, which will take us for a few days to get through that also. That will take us to the middle to the end of next week. And like I said, that will be pretty much it for what we're going to do here. So I'm sort of steering towards the end of next week to be completion of this class. That gives us 1 week left that you can pretty much have some free time to do what you have to do for other classes. All right, we'll work with this as we go forward. Solutions are posted for you. The rest of the time is yours.